Hello everyone and welcome to Calc Lesson number 25. Today we are going to be continuing on with related rates, today focusing on rectangles, cubes, and cones. So let's just jump in with our first problem. This says the length of a rectangle is decreasing at a rate of 2 centimeters per second, while the width is increasing at a rate of 2 centimeters per second. When the length is 12 centimeters and the width is 5 centimeters, find each of the rates of change of each quantity below. So there's going to be 3 parts. Starting with A, we're going to find the rate of change of area. So remember, a rectangle has a length, that's a horrible rectangle. Remember, a rectangle has a length, which I'm going to denote as L, and a width, which I'm going to denote as W. Now, we want to find the rate of change of the area, so we're going to need to be using the area of a rectangle, which hopefully we remember is just length times width. Let's go ahead and list what we know from our problem. It says the length of a rectangle is decreasing at a rate of 2 centimeters per second. So the length is decreasing, so that's the rate of change of the rate of the length, dl dt. And since it's decreasing, we can go ahead and list it as negative 2 centimeters per second. While the width is increasing at a rate of 2 centimeters per second, so dw dt equals 2 centimeters per second. Then it says when the length is 12 centimeters and the width is 5 centimeters. So L is going to be 12 centimeters and W is going to be 5 centimeters. Then we're going to find each of these quantities. So we're going to be using these 4 known quantities for both A and B. For A, we're looking at the area, so we have A equals L times W. To differentiate this with respect to T, the derivative of A, of course, is dA dt. And then to differentiate L times W, we do get to use the product rule. Product rule says first times the derivative of the second, so our first is L, and the derivative of the second would be dW dt, plus our second W times the derivative of the first, dL dt. Now that we've differentiated, we can go ahead and substitute what we know to solve. So we're still looking for dA dt, that's what we want to find, is equal to filling in our 12 centimeters, and dW dt is 2 centimeters per second, plus W is 5 centimeters, times dL dt is negative 2 centimeters per second. We are left with dA dt equals 12 times 2 is 24 centimeters squared per second, plus, and then we have 5 times negative 2, which is a negative 10 centimeters squared per second. So we can write dA dt as 24 plus negative 10 is just 14 centimeters squared per second. In part B, we also want to find the perimeter, or the rate of change of the perimeter. So still using the same rectangle and those same 4 quantities, but now we want to change the equation that we're using because we want to look at perimeter. And the perimeter is, remember, you add up all of the sides. So here, opposite of L would be the same length and the same width. So we can write our perimeter as 2L plus 2W. Differentiating, we get dP dt equals, the derivative of 2L is just 2 dL dt, plus the derivative of 2W is just 2 dW dt. Filling in what we know, dP dt is equal to 2 times dL dt is negative 2 centimeters per second, plus 2 times dW dt is 2 centimeters per second. So dP dt is equal to negative 4 centimeters per second plus 4 centimeters per second. So dP dt, the rate of change of the perimeter, is actually 0 centimeters per second, which, if you think about it, makes sense since our length is decreasing at the same rate as our width is increasing. Okay, continuing with part C, we're looking at the same problem. However, now we want to find the rate of change of the length of the diagonal of the rectangle. So looking at the diagonal, when we draw that diagonal, I'm going to call it Z, and we're actually looking to find dz dt. So what we notice, hopefully, is that we've created, with those three sides, a right triangle, which means the equation we can use to relate these three sides, just like we did a ton yesterday, is Pythagorean theorem. So I can write this as L squared plus W squared equals Z squared. And differentiating with respect to t, hopefully you remember from yesterday, we get 2L dL dt plus 2W dW dt equals 2Z dz dt. Factoring out a 2 and canceling, we can simplify this to be L dL dt plus W dW dt equals Z dz dt, and that's what we're looking to find. So now we can actually go ahead and plug in everything we know. Plugging in L as 12 centimeters times dL dt as -2 centimeters per second, plus plugging in W as 5 centimeters and dW dt as 2 centimeters per second equals, once again, just like yesterday, we run into that dilemma where we need to plug in a Z, but we don't have one, so we can actually plug in the values we were given for for L and W into Pythagorean theorem. So we have 12 squared plus 5 squared equals Z squared. And you might recognize this as a Pythagorean triple, where we get Z equals 13. So we can continue by plugging in Z as 13 centimeters, and then dz dt is what we are looking for. Multiplying, we get 12 times 2 gives us -24 centimeters squared per second, plus 5 times 2 is 10 centimeters squared per second, equals 13 centimeters times dz dt. Simplifying our left-hand side, we get -14 centimeters squared per second equals 13 centimeters times dz dt. Dividing both sides by 13 centimeters, we can write dz dt, the rate of change of the diagonal, as -14 over 13 centimeters per second, and we could also say dz dt is approximately 1.08 centimeters per second. So you can leave the exact, or you can round to 2 decimal places to your nearest hundredth. Okay, so let's move on with number 2. It says the edge of a cube is expanding at a rate of 2.5 centimeters per second. How fast is the volume changing when the length of an edge is 15 centimeters? And then bonus question, how fast is the surface area changing at the same time? So the first thing we want to do is just recognize that a cube is a three-dimensional object where all of our side lengths are the same. So up here in the top corner, you have my extremely poorly drawn cube, just noting that all of these side lengths are the same, so I'm labeling them all as x, the length, the width, and the height. So to start, for our first question, we want to find how fast the volume is changing, so we need to use a volume equation. Usually, volume would be length times width times height, but in this case, it's x times x times x, or just x cubed. Let's go ahead and list what we know about this problem. So it says the edge of a cube is expanding at a rate of 2.5 centimeters per second. So that means that x is changing, so dx dt is equal to 2.5 centimeters per second. And then we care about what's happening when an edge is 15 centimeters, so when x equals 15 centimeters. What we're looking for in this first part is how fast the volume is changing, so dv dt. So we can go ahead and differentiate our volume equation. So the derivative of v with respect to t is just dv dt equals, using our power rule, we get 3x squared dx dt. From here, we can go right ahead and plug in what we know. So we have dv dt equals 3 times x is 15 centimeters squared times dx dt is 2.5 centimeters per second. Simplifying, we get dv dt equals 3 times 15 squared times 2.5 is equal to 1,687.5 centimeters cubed per second. Don't forget though, we got a bonus question in this problem, so I'm going to go ahead and split almost all of my boxes, but I'm going to leave that known quantities because those are going to be true for both. So now we want to look at the surface area. So we want to think about the surface area of our cube. So the area, or think about a cube as being a six-sided figure where each face is a square. So we have the surface area of each of those sides would be x squared, and then we have 6 of them. So the area of a cube is just 6x squared. We know that those same values are true, so we can go ahead and identify that what we want to find is the rate that the area is changing. So dA dt, differentiating our formula with respect to t, we get dA dt equals, keeping our 6, bringing our 2 down, we get 12x dx dt. Plugging in what we know, dA dt is equal to 12 times 15 centimeters times 2.5 centimeters per second. So dA dt is equal to 12 times 15 times 2.5 gives me 450 centimeters squared per second. Okay, numbers 3 and 4 are a little bit different. Now we're going to be looking at a cone shape. So number 3 says water is pouring into a conical tank. So that means a tank that's shaped like a cone. So I'm just going to get a little picture going on this side here. Here is my cone at the rate of 8 cubic feet per minute. If the height of the tank is 12 feet and the radius of its circular opening is 6 feet, so that means we have in total a 12-foot tank, and at the very top our radius equals 6 feet. How fast is the water level rising when the water is 4 feet deep? So here we want to be looking at the volume of a cone. Volume of a cone formula is V equals 1/3 pi r squared times the height. So let's start, as always, by listing what we do know about this problem. It says water is pouring into a conical tank at a rate of 8 cubic feet per minute. So that is the rate of change of volume, dV dt, is 8 feet cubed per minute. Then it tells us that the height of the tank is 12 feet and the radius of the circular opening is 6 feet, but that's all about the tank. And that's not really about the water that's being poured in. So then we want to know, how fast is the water level rising? So that's our question, is to find dH dt, the rate of change of the height of the water, when the water is 4 feet. So here, this is our h value. So they're telling us that h equals 4 feet. That's everything that we got out of the problem. So the two things in red are what's relevant to the water being poured in. Notice that we don't have any information about the radius or the rate of change of the radius, other than the fact that the tank has a radius at the very top of 6 feet when and the total tank is 12. So the next step in a case like this is to actually write out r in terms of h. So we want to go ahead and create an equation for r in terms of h. To do that, what we know is that when the tank is 12 feet and r is 6 feet, so I'm going to set up a proportion. I'm going to write h over r is equal to 12 over 6, and then I'm going to cross multiply so that I can solve for r. So I get 6h equals 12r. Dividing by 12, I would get r equals 1/2 h. Now the reason we've done that is so that we can actually go ahead and rewrite our volume formula. So I'm going to take over a little bit of this box, and I want to rewrite the volume formula, replacing r with 1/2 h. So I'm going to write this as v equals 1/3 pi, and then instead of writing r squared, I'm going to write the quantity 1/2 h squared times h. Now I'm going to simplify this, so this becomes v equals 1/3 pi times 1/2 squared is 1/4 h squared times h. And then finally simplify that all into one, so I get my volume formula as v equals 1/12, multiplying the 3 times 4 together, pi times h cubed. So now we've completely rewritten this volume formula in terms of the ratio of the radius to the height of our current tank, and now we are able to solve the problem with only the information that we have. Now that we've done that, we can go ahead and differentiate with respect to t our new volume formula. So differentiating with respect to t, we get dv dt equals 1/12 pi is just a constant. Bringing down our 3, we would get 3/12 pi, or 1/4 pi. H to the 1 less power is squared times dh dt. And this is positive because now we see that we actually have values for dv dt and for h, and we'll be able to solve for dh dt, whereas if we had tried to differentiate earlier when we had an r in our equation, we would have needed to know the rate of change of r, and we wouldn't have had nearly enough information. So now we can go ahead and plug in. So plugging in for dv dt, we get 8 feet cubed per minute equals 1/4 pi times h squared, so 4 feet squared times dh dt. So we have 8 feet cubed per minute. That's not an m. Equals 1/4 pi times 4 squared is 16. So we have 16 over 4 is just 4 pi feet squared, dh dt. Dividing both sides by 4 pi feet squared, we get dh dt, the rate of change of the water level, is equal to 8 over 4 is just 2 over pi, and then feet cubed over feet squared leaves us with feet per minute. So the cone problems can be a little bit tricky because you have to start by creating a ratio of your height and your radius of your tank so that you can then update your volume formula in order to be able to differentiate and then plug in. Okay, our very last problem of the day. Here it says sand is falling off a conveyor belt at a rate of 12 cubic feet per minute into a conical pile, so shaped like a cone. So what's happening is the sand is falling off a conveyor belt, and then it's turning into a pile that's like a nice upside down cone. I'm sure you've seen sand fall like that before at the beach. It says the diameter of the pile is 4 times the height. Remember, that's about the whole pile. That's just like the information we got about the tank in the last problem. Not about the sand that's actually falling, but about the overall structure. At what rate is the height of the pile changing when the pile is 10 feet high? So let's go ahead and fill out that we want to talk about the volume of our cone shape, which means we're going to initially be using that volume equals 1/3 pi r squared times the height formula, but just like in the last problem, we are going to have to update that formula using the ratio that we find. What do we know about this problem so far? Well, we know that the sand is falling at a rate of 12 cubic feet per minute. So the change in our volume, dV dt, is equal to 12 feet cubed per minute. And we also know that we're looking for the rate of at what rate is the height of the pile changing. So we're looking for dH dt when the pile is 10 feet high, so when h equals 10. Just like last time, we don't have any information really about our radius at all or the rate of change of our radius, so we're going to have to create that ratio and then replace r inside our equation. So highlighted in yellow, we have the diameter of the pile is 4 times the height. So let's turn that into a number sentence here. We know the diameter, d, is equal to 4 times the height, or 4h. But we don't care much about d, we care more about r, the radius, and we know that a diameter is just 2 radii. So I'm going to replace this with 2r equals 4h, and then solving for r, I get r equals 2h. Just like in the last problem, I'm going to actually go ahead and rewrite my volume formula, replacing out that r. So I have volume equals 1/3 pi, and instead of r, I have 2h squared times h. So I'm going to simplify this as volume equals 1/3 pi times 4h squared times h. So we can write our volume formula as v equals 4/3 pi times h cubed. Now that we've rewritten our volume formula, we can go ahead and actually differentiate with respect to t. So we get dv dt equals 4/3 pi is just a constant, so it stays, but bringing down our 3, those 3's are going to cancel, and we're just left with 4 pi. H to the 1 less exponent, so that would be squared dh dt. Now that we've differentiated, we can go ahead and plug in what we know and solve. So we know dV dt is 12 feet cubed per minute is equal to 4 pi times h, which was 10 feet squared, and then we're looking for dH dt. So we have 12 feet cubed per minute is equal to 4 times 10 squared. So 10 squared is 100 times 4 is 400. We still have that pi feet squared times dH dt, dividing by 400 pi feet squared on both sides. We are left with dH dt equals 12 over 400 pi, which reduces down to 3 over 100 pi. Feet cubed over feet squared leaves us with just feet per minute. So again, a similar process to what we've been doing over the past few days, with that added step of having to rewrite our formula in terms of just h. Really great job with these problems today. You can go ahead now and complete homework number 25 in the 2.6 related rates homework packet. And as always, if you have any additional questions, you can reach out to your teacher.